Today, we are going to talk a little bit about wave interference, the principle of superposition. We're going to talk what happens when a wave hits a boundary. We're going to talk specifically about reflection of waves at boundaries. And all of this is going to set us up for the next couple of days where you're going to read about, and then we're going to see some examples of in a video, standing waves and standing wave patterns, especially on strings. So I want to let you know that I have posted the simulation you're looking at right now, this O-Physics Interactive Physics Simulations website. I have posted a link to it in your folder, in our Waves folder, in our unit folder on Schoology, so you can mess around with this or any of these others anytime you want. And certainly you can replay this video from time to time. I'm going to try and keep it short. I don't intend for this to be everything you need to know, but I want to talk about some important terms and some key concepts, and then I'll let you mess with it and then go back and reread the section of the book I asked you to read, and then play with this some more at your leisure. So, first of all, wave pulse interference and superposition. First of all, we're talking about wave pulses here. We're not talking about repetitive or periodic waves. We're talking about single wave pulses, or as you can see on the screen, in this case, two wave pulses. And we're going to look at what happens when these two wave pulses try to occupy the same space at the same time. Now, this is a really interesting phenomenon of waves. Uh, Regular particles can't do this, right? If a particle, or two particles rather, try to occupy the same space at the same time, they bounce off of each other. There is a collision. We talked about this first semester in our momentum unit. When two objects try to occupy the same space at the same time, they are not able. But waves are really just energy moving through a medium. So when waves occupy the same space at the same time, they do this thing called interfere with each other. And here is an example of that. Watch these two wave pulses as they approach and then move through each other. You can see at the point when they are at the same place at the same time, they interfere, in this particular case, constructively. They interfere constructively to build a bigger wave pulse, and then they continue moving on through each other. Now, watch what happens when I stop it at a convenient point here. Watch what happens when I change the height of one of the pulses and make it a trough, right? So over here on the left, we have a crest, and over here on the right, we have a trough. And watch what happens now when they take up the same space at the same time. You can see that they at least partially cancel each other out, only for a moment. That is a different kind of interference. This is called destructive interference because they at least partially destroy each other. So you have destructive interference when they are opposite each other, a crest and a trough, or constructive interference when they are both two crests or, of course, two troughs. All right. Okay, I'm going to go to a new simulation now. Let's see if I can find it up here. All right. So in this particular simulation, you see a lot of the same thing, all right? And you can do up here what we did before, okay? But down here, you can start to see what happens when you have multiple pulses moving through each other. Because yes, this up here is interesting when you have two individual wave pulses that are interfering constructively, or as I did before, interfering destructively. But what happens when you have a more periodic wave, more of a series of crests and troughs that interfere with each other? You can see that it creates a very interesting interference pattern. You get some alternating constructive and destructive interference at points, and all of it depends on whether it's a crest interfering with a trough or a crest interfering with a crest, and all of that. But this is known as the principle of superposition. The fact that these crests add to the other crest to make a larger crest, crests add to troughs to cancel out, or troughs add to troughs to make a deeper trough. Okay, so you can read through this when you take a look at all of these. All right. Now, what this is leading to requires some sense of what happens when a wave pulse hits a boundary. And this particular simulation shows us what happens when a wave pulse reflects off a fixed end or more rigid medium boundary. Now, this happens if the medium, the string, for instance, is attached to the wall. It also happens if, say, for instance, a thin string is attached to a thick string. There is a boundary, technically, between a thin string and a thick string if two of them are tied together. And when that pulse hits that boundary, some of the wave energy will be reflected. And you can see from this particular example, it's going to be an inverted or flipped upside down reflection. Okay, you can see that some of the wave energy reflects back, shows the example of the pulse reflecting off. The reflected wave is inverted. So it comes in on top and it comes back out on the bottom. Now that's with the reflection off a more rigid medium. That's usually what we're going to be dealing with. But you might ask, well, what if it's less rigid? What if it's a loose end? Well, you still get a reflection, but it reflects back not inverted, upright, we say. Okay, so it is on the same side of the medium as the original pulse was. But these reflections happen at any boundary, at any change in the medium. When you go from a string to the wall, when you go from a light string to a thick string, or a thick string to a light string, or any change in the medium, you always get some energy reflected. And the type of reflection depends on whether it's fixed or free. Now, what we're going to be looking at particularly is these fixed in reflections. What we're going to be talking about the next couple of days is what happens with a fixed end reflection. All right. All right, one last simulation that I want to talk about here and share some terminology with you. It is this one, interference and superposition 2. Come on now. There we go. All right. Now, what I want you to imagine is that this top, it says red wavelength, this top series of wave pulses, really a periodic wave with a given wavelength, is going to be moving in one direction. And then this blue series of wave pulses, really also a periodic wave, is going to be moving in the other direction. All right. So watch what happens when these two wave pulses moving in opposite directions start to interfere with each other. And what you have down here is the interference pattern. Okay. All right, oops, I got to get them moving in opposite directions here. All right, that's not what I wanted. Here we go. Okay. Here they are moving in opposite directions. Okay, so you see the red one moving to the left and the blue one moving to the right. And down at the bottom is the interference pattern. And you can see whenever a crest hits a trough, you can see there's a disappearance down here. And whenever a trough hits a trough, you get a really deep trough down here. And I think you can click on this and you can see them more clearly working together. Okay. All right. But this is the kind of thing that happens when you set up a periodic wave in a string, because now let me change them all to the same wavelength. Because when they're all the same, they interfere with each other in a very special pattern. All right. When they were different, what was going on down here was kind of chaotic and unpredictable. I mean, you could predict like the two crest would make a bigger crest, and so forth. But this, it's kind of a mess. But when all of a sudden these two waves are interacting with each other and they're the same wave, just moving in opposite directions, you get this sort of pattern. All right. And tomorrow you're going to read about, or I should say Thursday, you're going to read about. And Friday, we're going to see some more video examples of this. A link to a video I'm going to post on Friday that talks about the kind of wave pattern that is formed when you have two pulses moving in opposite directions that are similar to each other. Okay. So, because of the reflections, because of what happens with reflected waves, and because what happens with interference, constructive and destructive interference, you get this type of wave pattern. And on Thursday and Friday, we're going to talk more. You're going to read and see more about this type of wave pattern. And here's the sneak preview: standing wave. That's what we're talking about here. There's some sort of standing wave, and you'll see more about that on Friday. All right. Thank you.